Good morning to all of you. Dr. Emmanuel ALAMU and myself, Fabrice DAVRIEUX, want to thank AfricaYam Project for giving us the opportunity to present our main activity within RTB Foods project. So which means development of near-infrared spectroscopy for quality traits characterization. So I will present the principle of NIRS and the related opportunities and main challenges, and Dr. ALAMU will present some applications to YAM as well as the main opportunities and challenges. We all know the relation between color and taste. The color of a product recorded by eyes or instrument is a result of a selective light absorption, which depends on the chemical composition of the product. Spectroscopy techniques refer to the interaction between light, electromagnetic radiation, and matter. NIRS refer to the part of the electromagnetic spectrum, range between 400 nanometers and 2500 nanometers. And it is based on the interaction between vibrational property of the chemical bonds and the electromagnetic radiation. According to quantum theory, there is absorption of the energy of the radiation when this energy is exactly equal to the gap between two levels of energy of the chemical bonds. The quantity of energy absorbed is proportional to the concentration of the compound. So it's Beer-Lambert law. An absorption spectrum is the sum of all elementary absorptions of all the constituents of the product: water, fat, protein, sugar, and so on. Absorption spectrum represents the quantity of light absorbed as a function of wavelengths. And here you can see one spectrum with 9 wavelengths, and it can be summarized in one table with the wavelengths here and the percent of light absorbed at each wavelength. But it can be seen as a plot of absorbance as a function of wavelength as well, like this. This is similar to this, same information here and here. And spectrometers are used to measure the absorption at each wavelength, and spectra are complex with a lot of information, a lot of data. For example, a single spectrum on a FOS instrument corresponds to 1050 individual absorbance values, and for an ASD instrument is 2051 individual values of absorbance for one sample. This table in the background corresponds to the absorption data for 100 samples scanned on the FOS spectrometers. The size of the table is 100 rows and 1050 columns. So 100 rows like this with the samples and 1050 columns with all individual absorbance value in each cell. So each cell of the table corresponds to an absorbance value for a specific wavelength. So welcome to the spectral matrix, what we call the spectral data matrix, with all the information about all the sample and all absorbances at each wavelength. So the art of NIRS is modeling or calibration. From the spectra, the absorbance value are converted in matrix form, and using chemometrics, multivariate analysis, in fact, they are combined with physical or chemical property measured on the same samples. And the goal is to develop a model that will predict the Y property of new samples according to their spectral fingerprint. So from this, we want to predict Y directly. So NIRS is a non-destructive technique, so you don't have to extract the compounds and quantify the compound to do the characterization. So it's the non-destructive techniques. It's multi-criteria at the speed of light. Once you have done the calibration, you can predict dry matter, protein, fat, sugar, everything in one shot. We can work on raw or processed products. It's a qualitative and quantitative characterization. You can do both of them. But NIRS require a database representative of the product. So we need to be robust. We need to be a representative of the different sources of variability of the product. And this technology is based on a rigorous standard operation procedure for measurement. So from sample preparation to database management. And this approach needs a strong and fair link with laboratory. Same sample, same objective.
Yeah, thank you, Fabrice. You are welcome once again to this presentation. I'm going to take you through the application of NIS in yam quality phenotyping. Then I will also add some points on benefits or opportunities and the challenges on using NIS in yam quality phenotyping. Among the high throughput phenotyping procedures available for yam improvement breeding programs, near-infrared, which is NIS, has excellent potential for simultaneous prediction of various quality traits, as Fabrice mentioned earlier. The established correlation to highly reproducible procedures, such as chromatography techniques and other laboratory techniques, has made it an easy tool to apply when we are correlating the values from the high laboratory techniques to NIS spectral data. So it makes it easy for us to apply NIS for yam quality phenotyping. The analytes that have been reported by various NIS studies on yam tuber qualities, they range from proximate to bioactive components, and which include carbohydrates. Under carbohydrate, we have the sugar, and we have the polysaccharide, we have the starch, we have amylose, then we have the soluble sugar and the cellulose. So we have protein, we have fat, minerals, crude fiber, and secondary compounds such as tannin and flavonoid and phytate, which are referred to the bioactive component. The prediction models are developed for these quality traits, and then the performance of these models are reported for individual parameters using the determination coefficient, regression determination coefficient between the predicted values and the laboratory values, which is referred to reference values. So the R square is what is being used to measure the accuracy of the predictions. Here from the chart and from the table being presented here, we can see that most of the parameters being evaluated have a good R squared, and that means we can use NIS conveniently to predict the yam quality in the laboratory. There are accurate predictions of R squared of greater than 8. Moisture is 1. If you look at it, total sugar is another one. We have starch, which is another one. We have polysaccharides. We have soluble sugars, and we have protein, total nitrogen. We have dioxin as well as the flavonoids. On the other hand, we can really mention that there are some that the R square is very low, but they can be improved. We are working on them to improve them. On the prediction of amylose, cellulose, crude fiber, tannin, fat, ash, the fatty content, they prove less reliable. Yeah, actually this information were obtained from our paper that's been reviewed and then we've been published on the TB Foods and IFST journal. There's one key example I want to present to us here, based on the work being done in the IT on yam quality phenotyping. Working on fresh and or blended or intact tubers in the laboratory or straight in the field with a portable spectrometer, it has a potential to speed up the spectral acquisition, especially when we want to take the full advantage of NIS as a high throughput phenotyping tool for rapid screening and selection in breeding. The key point there is the sample preparation, because in the laboratory, when we want to run the reference value, we usually subject the sample to different processing forms and therefore increase the time of analysis, and which make the result to come out at a low speed. Therefore, we cannot achieve the high throughput aim that we are planning to achieve. So sample preparation is a prerequisite for the prediction of quality trait by NIS. Sometimes it's a big challenge when large population of breeding materials have to be evaluated. For example, and for yam, we need to dry them at either oven dry or freeze dry, and we take 2 days at least. There is a limiting step for high throughput sample analysis. So therefore, we look at the feasibility of analyzing the fresh yam without drying. It is important that the fresh materials are being used in cassava for carotenoid analysis, and then from dry matter and so on. So we try to extend it to yam and see the feasibility. So we want to look at how we can use the fresh yam without drying, and then we can still measure some quality traits, apart from dry matter. So what we did is we used 200 clones, and which representing the D rotundata and D alata together. They are grown in 2 locations, Ibadan and Ibiaja. These materials were collected from the yam breeding unit of ITA, and so the samples were split randomly into 2 sets, and we classified them to be calibration and the validation set. The calibration set consisted of 150 clones, when the cross validation set contained 50 clones. So we used three methods to prepare the samples. The 3 different methods involved chopping and the grating, as well as the blending. So the 3 methods that were used produced 3 different types of samples, and then the spectra of each samples and the reference data the spectra of each sample and the reference data were used to develop the calibration model. We use a modified partial least square approach, and using WinSI software. So what is the result? I'm just summarizing the result here because of time. The regression coefficient of determination, as I mentioned, is measured the accuracy of prediction. So the higher the R-square, the better the prediction of the model. So in this case, we use 3 methods, and then we use 3 parameters, as I've mentioned: dry matter, protein, and starch. So we could see from this particular chart that been shown, we can see that for dry matter, we can see that the blended is the highest, followed by the grated, and then the chop is the last. So for protein, it follows the same pattern. The blended has the highest, followed by protein, and then followed by the chopped. But when we come to starch, it's a little bit different pattern. We have the starch, which is 0.83, followed by the chopped, then the grated. So we could see that blended had a better prediction than the chopped and the grated for dry matter starch and protein. So protein had a weak prediction across the 3 sample preparation methods with very low R square. But another statistics parameters which shows the ratio of performance shows that yes, this may be low for protein, then it can be improved. So it can be improved. So Fabrice has mentioned some of these benefits and opportunities. I just want to add to it and also to add to the challenges which we are facing in this. And another point I want to add to what Fabrice says is the minimal sample preparation is needed. So in this, we have minimal sample preparation. It's just you can analyze using raw samples. And then the analysis time is very short. Within few minutes, you have completed acquiring your spectral data. Once the calibration model is there, then you can get your values. It is very cost effective, and then especially when you are analyzing a single or large batches of sample, and results are usually precise and accurate, and the fewer steps are involved in the analysis, unlike the wet laboratory method, which involves series of steps. And another important point is the use of hazardous chemical reagent, which is completely eliminated in this, except when we want to generate the reference value. Once the reference value is being generated, the calibration is being developed, we don't need to use or expose to the chemical reagent. And one other challenge is one of the challenges I want to mention, also in addition to what Fabrice mentioned, is nature of the end product. It's very difficult in predicting quality traits of end products, especially those that have been derived from the chemical reactions and interactions during processing. So with all these opportunities and challenges, we still believe that NIS has a very good potential to be applied into yam quality phenotyping, and then it can give accurate and very precise results. I want to acknowledge on behalf of the Work Package 3 teams and Fabrice, which is a co-presenter. We want to acknowledge our founder, Bill and Melinda Gates Foundation, and then also to acknowledge AfricaYam Project, which is a partner in this training workshop, and want to acknowledge UAC FSA Benin and the entire Work Package 3 teams, which includes the NACRI, the IITA, the NRCRI, the SIP, the SIAT, the NAR, CIRAD, and INRAI. And finally, we need to express our gratitude to RTBfoods, PMU, for their support and for the excellent coordination of the project. Thank you very much. So thank you for listening.